afternoon, my name is Kate Schutz, and today I'm going to talk about the Lab 4 experiment I performed. First I'm going to talk about the purpose and method, then my observations and calculations, then the code I created to make a simulation of the experiment, then I'll give a little bit of an interpretation of the simulation, and finally I'll give the conclusion and results of my experiment. So the purpose of this lab is to create a simulation of the current flowing through a metal tube when a magnet is dropped through it. I use several principles including Faraday's law, the general Biot-Savart law, and Newton's second law. Here are the formulas I used in my code to create the simulation. The method of this experiment was that first I videoed myself dropping a bar magnet down a tube of aluminum foil. I analyzed the video to find the time it took for a magnet to go through the tube. I repeated this process 6 times and took an average of the time. I used different attempts and changes in I used this average in my code calculations and for my simulations. What I did was I compared the time it took for the magnet to drop in the simulation to the average time I calculated. The next step I took in this experiment was to create a simulation that represents the magnitude and direction of the current induced on the tube in this experiment. To make this code, I first created a graph that would graph the velocity of the magnet versus the time and set up some initial variables, including the geometry of the tube, which I found by measuring the aluminum foil tube I used with the meter stick. I also initialized some numerical parameters of the simulation. Next, I created the aluminum foil tube for the simulation. Then I set some initial values for the mass of the magnet and the magnitude of the magnetic dipole, which I found in the previous lab. I created a visualization of the bar magnet, and I also set the initial velocity and time of the magnet both equal to 0. And then on lines 98 through 102, I used the general Biot-Savart law to calculate the magnetic field of the bar magnet. To calculate the flux of the tube, I split the tube into n rings and then calculated the derivative of the flux over time at each ring using Faraday's law. So next I created a simulation loop. That predicts the motion and visualization of the current. I then calculated the current in the ring by dividing the derivative of the flux over time by the resistance of the tube. Next, I calculated the magnetic field at each ring of the tube and the magnetic force of the magnetic field on each ring. I then determined the magnetic force on the magnet by adding each magnetic force on each ring together. Lastly, I determined the velocity of the magnet at each ring and the position of the magnet at each ring using Newton's second law. So here's what I did there. And then here is a video of my simulation. So next I want to answer a few questions. So the first one is that the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate the current flowing in opposite directions. Which color corresponds to the clockwise direction as viewed from above? And which counterclockwise? How can you know? I know that the bar magnet, north pole, is facing downward when falling through the tube. That means the magnetic field is going to be in the negative y direction, and the velocity of the magnet is going to be moving in the negative y direction also. Knowing this, I can determine the induced current is moving in the clockwise direction when looking at the tube from above using Lenz's law. This current created by the magnet should be represented only during the magnet's motion and therefore represented by the blue ring. The red ring represents a counterclockwise current that is caused by the magnet when it is moving and stationary. The next question is, what happens to the dynamics of the system when you flip the magnet around? When you flip the magnet around, so the south side of the magnet dipole is falling headfirst and the negative y direction, you reverse the direction of the induced current and the current caused by the stationary magnet. So the induced current caused by the magnet and the motion of the magnet is going in the counterclockwise direction, and the current caused solely by the magnet is flowing in the clockwise direction. The third question is, how does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? The time in the tube is actually very similar to the time I calculated from the experiment. Both are around 0.31 seconds. I do think, however, that the computational model could be made more accurate by taking into account air resistance. The fourth question is, what does the shape of the velocity versus time plot tell you about the forces acting on the magnet? The shape of the velocity versus time plot tells us that the force acting on the magnet increases with the velocity of the magnet. The last two what if questions is, what if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? If the resistivity of the conductor was reduced to zero, then the magnet of the induced current would equal the flux, and the magnet would take longer to fall down the tube. What if the holes or slots were cut into the tube? How would this affect the rings in the current model? If holes or slots were cut into the foil, there would be less material, which means the induced current would have a smaller magnitude. If the induced current has a smaller magnitude, then the force of the magnet is also smaller, therefore the magnet would drop faster. So this is what I found during my lab 4 experiment. Thank you.